Hello my dear students, today we are in lecture number 18. Lecture 18 of chapter 1, Electrostatics. I am B.S. Pandey student. Today we will start the next chapter also here after few minutes, but before starting that chapter we are going to conclude the last topic of this chapter. It is the distribution of charge on plate, that is the charge distribution on plates. Okay student, for this particular topic student, you have to bear in your mind the first thing you have to remember, the first point: conservation of charge must obey okay. Suppose this is the plate of charge Q1 and Q2. Okay, you have to show the distribution of charge on both the faces, on plate 1 and plate 2. On both the faces you have to show the charge distribution. For the charge distribution, the second point you have to bear in your mind, it is the total charge of the system must be find out. It is the Q total of the system, it is Q1 plus Q2, because we have to apply the conservation of charge, it is Q1 plus Q2. Now the average charge will be distributed on both the outer face will have equal charge and same nature. My dear student, it means if it is the total charge, then the charge equally divided on outer faces of the plate. These are the outer faces. It means we have to give Q1 and Q2. Okay, here Q3 and Q4. Q3 and Q4 are the inner faces and Q1 and Q2 are the charges on outer faces. So the Q1 will be equals to Q2. Remember, in magnitude and nature both. And it is how much? It is the average charge. So the average charge, it will be Q1 plus Q2 by 2, since we are having only 2 charges. So finally the plate looks like this one. A very simple concept student, so try to understand, and if you will have any doubt, you may ask, you may comment, you may come for the discussion. So here the Q1 plus Q2 divided by 2, and here Q1 plus Q2 divided by 2. What was the charge actually? Initially it was Q1 and Q2. Okay, now the next step, my dear student. The next point you have to remember, we are having the distribution of charge on the outer faces. Now we have to find Q3 and Q4. Okay, so the inner faces will have will have charge with opposite nature, which is very important, with opposite nature. It should be note down in your notes, which is very important, my dear student. And how much this charge should be, so try to understand. Here the charge was q1. Now we are having the charge q1 plus q2 by 2 here. So the here charge will be, since the charge should be conserved on each plate individually and of the system also. If it is q1 and here q1 plus q2 by 2, it means here the charge will be on this plate, charge will be q1 minus q1 plus q2 by 2. Okay, and on this plate the charge will be, if it was q2, then q2 minus q1 plus q2 by 2. Okay, finally we will have the charge. Kindly note down, these are the points which are the very important. We will do few questions and concept will be more crystal clear. Okay student, now we are having the charge on this plate and on this plate, as outer plates have the charge q1 plus q2 by 2, q1 plus q2 by 2, but inside the charges now here q1 and q2 are not present. Now we are having the new charges. Okay, so here the charge will be, since it is q1 minus q1 plus q2 by 2, so the 2 q1 minus q1, it will be q1 minus q2, q1 minus q2 by 2 over here, and over here the charge will be how much? It is q2 minus q1, and it is 2q2 minus q2, that is q2 minus q1 by 2. So this is the new charge distribution over the plate. I think we should have an example for more simplicity. So the one example, suppose my dear student, you have plates. It is the first plate and the second plate. Here 1 coulomb, and here suppose 3 coulomb. You have to show the charge distribution. Try to solve by yourself, otherwise I will solve this question. Now look at here for the solution and how much you have solved correctly. Try to find out. The second step, we have to sum up the charge. So the total charge will be how much? 4. So outer faces will have the same amount of charge, 4 by 2 coulomb, and here also 4 by 2 coulomb. Okay my dear students, initially it was 1 coulomb and it was 3 coulomb. Now the next step, here 4 by 2, it means 2 coulomb, but the total charge what was how much? The total charge was 1 coulomb. If it is 2 coulomb, it means we have to subtract minus 1 coulomb. Okay, minus 1 coulomb. As we have studied, both the inner faces should have opposite nature, okay, and equal amount. If it is minus 1 coulomb, so it should be plus 1 coulomb. It was 1 coulomb. You can see here we have total charge is 1 coulomb. Conservation of charge is valid. Now here, if it is 1 coulomb and it was 3 coulomb initially, so we have to find, if it is 1 coulomb, then how much should be outer, how much charge should be at outer face? Of course 2 coulomb. So that 2 plus 1, it will be 3 coulomb, and initially it was 3 coulomb. So again on this plate also we are getting conservation of charge is fully valid. I hope you understand. You can write over here also, here the charge, if it is positive, then it is negative of the same amount, minus q1 minus q2 by 2. Both are similar, you can see. Okay, now another example, student. This is your classwork. Okay, now we are taking 3 plates. Okay, suppose okay, 6 coulomb, 4 coulomb, and okay, 8 coulomb, so that calculation will be easy. Now try to represent distribute charge on each faces of the plates. Okay, my dear student, now I am solving. If you can solve, pause the video and try to solve. Now I'm solving. Here the total charge of the system. Okay, total charge of the system, how much? 6 plus 4, 10 plus 8. Okay, 18. So 18 by 2, here the 9 coulomb. 18 by 2, 9 coulomb. Outer face, actually I told you it is outer face, we are considering of only the outer plates. Okay, how many plates are placed in between the two outer plates, it doesn't matter. Okay, you have to see the two outer plates, 9 coulomb and 9 coulomb. Initially it was how much? 6 coulomb. If it is 9 coulomb, how much charge should be there? Of course 3 coulomb. If it is plus 3 coulomb, here it will be minus 3 coulomb. Okay, now how much charge was there? 4 coulomb. If it is minus 3 coulomb, how much charge should be there so that the charge will be 4 coulomb? Of course it should be how much? 7 coulomb. 7 minus 3, how much? It will 4 coulomb. If it is 7 coulomb, then it should be minus 7 coulomb on the inner face, minus 7 coulomb. If it is minus 7 coulomb and it is 9 coulomb, how much it will be? 7, and it will be the I think we had some mistakes. 6 plus 4, 10, 8, 18, and it is 9. Yes, then here, oh sorry, here the minus 3 coulomb na? Yes, it is minus 3 coulomb, and it should be the plus 3 coulomb. Okay, if it is plus 3 coulomb, how much? Plus 1 coulomb, and it should be minus 1 coulomb, and 9 minus 1 coulomb, it will be 8 coulomb. Again we are getting conservation of charge is valid, my dear students. Okay, there was some very simple mistake, you can see. Now student, another question I'm giving you for the homework. Okay, it will be your home assignment. Try to solve by yourself. Okay, so I'm taking for the homework again 3 plates. 3 plates. Okay, and suppose I placed, okay, 1 coulomb, 2 coulomb, 3 coulomb. It is 3 coulomb. You have to show the charge distribution on each faces of 3 plates A, B, C. Okay, A, B, C. So this is your concept of charge distribution on plates. Okay, student. Now my dear students, as we have almost finished this chapter, and questions and an assignment you should solve by yourself. So we should start today the next chapter, chapter number 2 of NCRT. Let me rub this. Now we are proceeding chapter 2. Okay, second chapter of NCRT. We have to focus NCRT accordingly. We can solve number of questions that is important for the competition also, but we will focus ourselves over the NCRT first. Now this chapter is called, of course in electrostatics, it is called the potential and capacitance. Potential and capacitance. Okay, my dear student. Today we will focus over the potential and potential energy. We will take introduction of potential and potential energy, and then we will move for the potential energy gradient. In next lecture we will study in a detail. Okay, so here the potential energy and potential. You are familiar with this word, student, the potential energy and potential, but today in this chapter we are studying about the electric potential energy and electric potential. Okay, my dear student. So the first you should write the definition of potential energy, that is the electric potential energy. Potential energy we will represent by U and then electric potential. Okay, and then we will move for the derivation and few interesting question, my dear student. So the electric potential energy, actually whenever we talk about the potential energy, we study the system of at least two particles. Okay, here we are talking about the charges, so in system we will have the two charges. For single or isolated charge, we cannot study the potential energy. Okay, we have discussed in very detail in gravitational chapter. Even in your standard ninth, you have been taught that potential can be measured of one particle of body, but the potential energy can be measured in reference with the minimum two particle of body. Okay, student. So write down the definition of potential energy. Actually, it is the amount of work done. Okay, amount of work done. Suppose you are having space and the one charge Q1 is placed over here and another charge is somewhere, suppose it is Q2, and this is the space that created by this particular charge within its field. Actually field goes to the infinity, but we are confined the field that read by the influence by that influence this charge Q2. Okay, my dear student. So it is the amount of work done. We are talking about the potential energy. Of course, this charge will either repel or attract this Q2 with the electrostatic force. So whenever you bring this Q2 at a certain point over here, okay, from somewhere, or you can say from infinity, in presence of this Q1 against the electrostatic force or by the electrostatic force of this Q1, which is placed at certain distance r, then this amount of work done, actually is called potential energy. Okay, again I am telling you, it is the amount of work done to move a point charge. It may be the point charge, you can consider this is as a point charge. The amount of work done to move a point charge from one point, here the one point we have been discussed, the infinity, okay, from one point to another against the electrostatic force or in favor of electrostatic force. So this is the definition of electric potential energy. You can write in your notes. Remember, from infinity you are bringing this charge, and this Q1 Q2 both we are considering here the point charge. Even this formula can be applied for the charge which is having the distribution charge, okay, distributed charge. But this formula will get we will get a formula that will be applicable for the point charge, and if the charge is not point, then we'll get the and we'll apply the integration, mathematical integration. Okay, now electric potential. Definition of electric potential. Electric potential. We'll represent this electric potential by V. Remember, student, since this is the work done, so the SI unit will be joule. Okay, the SI unit will be joule. Now the electric potential. Actually, when we talk about the electric potential, my dear student, okay, so the electric potential, the work done by an external force, remember, by an external force in bringing a unit positive charge from infinity to a particular point. It is the definition, perfect definition of NCRT, given in NCRT, and the same definition I'm telling you, okay. So it is the, again I'm telling you, if you want, you can write work done by external force in bringing a unit positive charge, okay, from infinity to a particular point. This is the electric potential. Now if you are having the space, look at here, I am correlating here the electric potential and potential energy, which is the very important, okay. I'm here at infinity and I'm bringing a test charge over here at point Q. Here the work done, since I'm not having another charge, here the work done due to this isolated charge, it will be considered as the potential. But another charge, if you will bring, suppose Q naught, this is also the point charge, Q naught, from again infinity, to make these two charges separate by certain distance. Now this amount of work done will be considered as potential energy. Why? Because you have to work against the field of this charge, or you have to work against the force, electrostatic force of this charge, or in favor of electrostatic force of the second charge, and then you have to write the relation as work done by or per unit this charge, work done per unit this charge, okay. Suppose you have work for 10 joule, but 10 joule per unit this, if it is the 1 coulomb, then 10 joule per unit this 1 coulomb, it will give you the potential. If you want to find out the total work done, that is the only 10 joule, okay, so the 10 joule will be the energy, but 10 joule per unit this charge will give you the potential. That will be the potential of isolated this charge, and this is the electric potential of which charge, of charge Q. At certain point of this charge, you have calculated the potential at point where this Q naught is placed. You are finding the potential of Q. By this formula, you are finding the potential of which one? Potential of Q at a point where Q naught is placed. It is very important, okay. So here you can write the work done, which is the potential energy. Remember, here this work done is nothing but the potential energy, because this is the work due to the system of charge, but this is the work due to the single charge. So this work can be written as the Q naught times potential by isolated charge. Now if you try to find out the here SI unit of potential, then you will have here for the work joule, and here for the Q naught it will be coulomb. So joule per coulomb will be the SI unit of electric potential. I don't think so this is a very confusing, students. It's a very simple. If you are having one charge at a particular space, whatever may be the electric field presence over there, and you are bringing from infinity the amount of work done to bring that particular unit positive charge from infinity to a particular point, is it called the potential. And if you are bringing a test charge from infinity in presence of any charge, that is, you have to do the work against the electrostatic force or against the electrostatic field, then that particular work done will be considered as the potential energy. This is the basic difference between electric potential and potential energy, my dear students. I hope you will be quite clear between difference between this electric potential and potential energy. Now, the one thing, the very important we'll discuss today, it is potential energy gradient. My dear students, potential energy gradient. In next class, we will study about the electric potential and its derivation. Okay. So, electric potential energy or the potential energy gradient. Potential energy gradient. The number of questions you will find in competition also by this topic. We know according to conservation of energy, my dear student, according to conservation of energy, you can write the change in potential energy plus change in kinetic energy. Change in kinetic energy must be how much? Yes, 0. In another word, you can say the sum of potential energy and kinetic energy must be constant, but the change in potential energy and change in kinetic energy must be equals to, according to work energy theorem, change in kinetic energy gives you the work done. Okay, if you're having a point charge and you are moving a point charge from one point to another point, if you are moving from one point to another point, so the change in kinetic energy, of course you have to do some work to change the kinetic energy, so the change in kinetic energy will be work done. And now using this equation into this one, you can write here the delta U plus delta K can be written as W, it is equals to 0. Mathematically it can be written as minus delta U, and delta U is nothing but the U final minus U initial, but we are having a negative sign, so this W can be also written as the U initial minus U final. Okay, we will use this equation in integral form also, my dear student. This is very, very important. Okay, but from this equation or from this particular line, we will find out the potential energy gradient. Work done, it is the force times displacement. F, for the very elemental study, for the very elemental distance we are studying here, the F dot dr is equals to how much? Minus delta r delta u. This is the partial operator. Okay, and this F can be also written minus delta u by delta r. This is the partial operator, and it is also represented as minus del u by del r. Remember, this del is representing here partial differential operator. Okay, how you have to differentiate, I'll train you how you have to differentiate, but this formula you have to write in this way. Overall, in potential energy gradient, my dear students, you have to write, since force is vector quantity, so the fx I, fy j and fz k minus del u by del x I cap del u, sorry, again minus del u by del y j cap minus del u by del z k cap. Here the u is a function of x, y, z, that is the function of space. This u is also the function of space. This u is also the function of space, my dear student. Okay, and this is the vector form of force. If you are finding the potential energy, a very quick, a very simple example I am discussing over here. Suppose if potential energy is given as x square y, okay, kx square y, k is constant, any positive constant, and you have to find the force. The question is to find the force. Okay student, how you will solve? In very quick, we are solving one question. Next class we will start from here. So the force x I plus fy j, since we are having the quantities only varying over x and y, so we are writing as the force on x and y. So k d x square y by del x plus k del x square y by del y. I and j will apply. Here the k, we have to find the differential of this function with respect to x. So x will be here variable, otherwise y will be constant. So the x square dx, it will be 2x I plus, now x will be constant and dy by dy 1 with j cap. So this is the fxi plus fyj, and in Newton you will get the magnitude also, student. So this is all about the today lecture. From here we will start the next lecture, my dear students. Thank you very much.